This is a question which follows on from the previous video where we actually found out that the magnetic field acting at a distance x away from an infinitely long and straight wire is equal to this. So you can watch the previous video if you want to see the full derivation. And what I will do now is look at this particular question where you have a similar situation. So there's an infinitely long and thin and straight wire. Now, next to this wire, there's a conductor, or the question calls it a copper rod of length L. So that's from here to here, and this is not infinitely long. This has a very specific length, which is given to us as b minus a, where a is the distance from the wire to the left end of the conductor, and then we have b as the distance from the wire to the right end of the conductor. And we know that this conductor is actually moving in this upwards direction with a constant velocity, v. And what we want to find is we would like to find the induced EMF in this metal rod. Okay, so let's see how we can actually approach this. Now, the first thing to note is that no matter where you are, in this plane, the value of the magnetic field will be given by this. So this point P will experience one magnetic field and point Q will experience a different magnetic field because the 2 points are at different distances away from the wire, which means that each and every point on this conductor, which look like this, which are separated along a horizontal direction, they all experience different amounts of B, right? So what we have to do in this case is just consider what happens at an arbitrary distance away from the wire, and I'm going to call that arbitrary distance x. And I'm just going to analyze that, at distance x, I have this bit of conductor whose length will be dx. So I'm going to zoom in and I'm going to, draw the conductor in this way. And then this bit from here to here, this is supposed to be infinitely small, but I'm just exaggerating for the sake of it. So this will be dx. And then after a very short amount of time, which we're going to call that short amount of time dt, this whole conductor will travel. So after an amount of time dt, the conductor will travel from the position on the bottom to the position on the top. That's the direction of motion. So this infinitely thin piece of conductor will also travel and it will have this new position. So this happens over a very short amount of time dt, right? And what happens in that short amount of time is that this this dx, this piece of conductor dx, will sweep a certain area. And we can find out what that area is, and we'll try to understand why that area is relevant in the first place. So if we start from the center line to the new center line, we'll end up with this kind of like rectangular section, right? And we can find what the area is of this rectangle quite easily. So we know that this rectangle has a width dx, and so let's call this d area. So it's dx, which is the width, times the length. So the length is just the distance traveled in the amount of time dt, which is just v dt. And that's it. So that's the area. And then the reason why we're looking at the area is because, remember, we're dealing with a magnetic field. So this point, which is at a distance x away from the wire itself, experiences a magnetic field which is given by the above formula. Right? So this point here is what we're looking at in this zoomed in diagram below. And the magnetic field here, dx, is given by this formula, which is mu 0 I over 2 pi x. Okay, so I'll write it here again. It's mu 0 I over 2 pi x. So we have the area, we have the magnetic field. So what we can do is we can actually find out what is the magnetic flux, right? So we know the magnetic field in this, in this area, everywhere in this area is pointing this way. So we can find out the flux. So the flux is equal to mu 0 I over 2 pi x multiplied by this, which is v dt dx. Okay, so that's the infinitely small flux, which only happens for this infinitely small element that's traveling a distance in an infinitely small amount of time. So what we can use this for is if we divide it by dt, we'll get d phi by dt on this side. And this is mu 0 I over 2 pi x, and then this is just v dx. Now this quantity will stand for the absolute value of the EMF, but only for this particular element. So what this means is, as this conductor is going to be traveling, the magnetic field due to this wire will induce an EMF within this tiny bit of element, and that EMF, that induced infinitely small EMF, will have this formula right here. So we have d epsilon will be equal to mu 0 I over 2 pi x v dx. Now, this is the EMF which is induced only in this element, but what we want to find is the EMF in the whole copper conductor. So what do we do with this equation to find that out? Well, we have to integrate, right? So we have that the total EMF would be the integral of the epsilon, which is the integral of mu 0 I over 2 pi x, and then we have v dx. So we're integrating with respect to x, where x is the distance from the wire to wherever we are on the conductor, right? So the conductor starts here, and this point corresponds to x equals a, and the conductor ends here, which is x equals b. So the integration limits would be from a to b. And unlike the integration from the previous video, this is going to be much simpler to do. So we have that the induced EMF will be mu 0 times I times V. So I'm just taking the constants out. And then we have dx over x. So again, this is a very straightforward integral. This is just the natural logarithm of x from a to b. And if you use the laws of logs, you'll see that this is actually equal to ln of b over a. So this is the total induced EMF in a conductor which is moving, perpendicular to an infinitely long and straight wire. And the reason we had to do the integration was because, remember, each point on this conductor is experiencing a different amount of magnetic induction, because magnetic induction away from a straight wire is inversely proportional to the distance from it. And that's the end of the question.